In this video, we're going to prove the following theorem. The linear congruence AX is congruent to B mod n has a solution if and only if the GCD of n in A divides B. And if D divides B, that is, if it has a solution, then it has D mutually incongruent solutions mod n. Okay, proof. We basically proved this already. AX is congruent to B mod n if and only if AX is equal to B plus, say, NY. If and only if, bringing the NY to the other side, if and only if AX plus N times negative Y is equal to B. Now, this is a linear Diophantine equation, and the only way it had the solution is if the GCD of those two divide B. Let's call this 1. Since 1 is a linear Diophantine equation, it has a solution, which we proved in a previous video. It had the solution if and only if that number B divides, as I said, the GCD of those two numbers. Divides the GCD. Actually, it's the other way. If and only if the GCD of A and N, which I'm calling D, happens to divide B. Now, we went on further to say that all solutions, so let's just kind of slow down a little bit. If x0, y0 is a solution to ax plus n times negative y equals b. Now remember, these three statements are exactly the same. Okay, so if I'm telling you x0, y0 is a solution to this, then x0 is the solution to the first congruence equation. A times x sub 0 will equal b mod n. They're the same exact statements, all three of them. Okay, then I'll show this again. Then x0 plus n over dt, comma, y0 minus, okay, we can get away with plus a over dt is also a solution. Now, why is that? Well, let's get our hands dirty and find out. It's supposed to be a times x plus n times negative y is supposed to be b. So a times x0 plus n over dt plus n times negative y, which is negative y0 minus a over dt. Well, let us see what this is. Now, we can distribute slowly. We can distribute the a with the xi plus the n with the negative y0. Well, that's b. Plus, here we have an over dt, and here we have, minus an over d times t. That's going to cancel out. This is equal to b plus 0, which is b. So, this here is our solution. Not going to prove that and t is an integer. Not going to prove in this video that those are all the solutions, or all solutions are in that form. I already did that. Now, what I want to prove is that it has d mutually incongruent solutions mod n. So, I did show that it is a solution. Now, I'm going to let t range from 0 to n minus 1. So, we have x0 plus n over t times 0, and we have x0 plus n over d times 1, all the way up to x0 plus n over d times d minus 1. Same thing for the y values. y0 plus n over d times 1, all the way up to y0 plus n over d times d minus 1. This may not be the greatest notation, but that's one solution where t is 1, t is 0, t is 0. This is the solution where t is 1, all the way to the end, where that's the solution where t is 1 less than d. There are d minus 1 solutions. The reason is 1, 2, 3, all the way up to d minus 1. That's d minus 1 numbers. But let's not forget to add on the number 0. Let's add on one more number and we get d. Now, why do I do that all the time? Because it's counting for us. 1, 2, 3, 4, d minus 1. Oh, that's d minus 1 numbers. Plus one more. It has d numbers. And I claim that that those are all incongruent. Now, let us suppose otherwise. Suppose that x0 plus n over d times t1, n over d times t1 is equal to x sub 0 plus n over d times t2, and this is mod n. Keep in mind that t1 and t2, let's say t1 is less than t2. I want to assume that they're different. Okay, so t1 is less than t2, and they're all between 0 and d minus 1. They're less than or equal to d minus 1, and t1 and t2 Well, T1 is bigger than 0. T2 can't be 0 because the smallest T1 can be is 0 and T2 is bigger. Okay, so we have this. Now, if we take away x0 from both sides, that's allowed. So now we have n over dt1 is congruent to n over dt sub 2, and this is all happening in mod n. Note for a moment that d, since d is the GCD of a and n, that implies that d goes into n. That is, these are integers. D divides evenly into n. N over d is most definitely an integer. Now, we have that the GCD of n over d and n. Well, this is an integer and this is an integer. Clearly, n over d goes into n over d. It goes in one time, and likewise, n over d also goes into n evenly. It goes in d times. So it turns out that the GCD is n over d. It can't be bigger than n over d because nothing bigger than this number goes into that number. If that number is 8, nothing bigger than 8 goes into 8. No number bigger than 8 goes into 8 evenly. So the GCD is that. Okay. Now, so you could divide by the GCD. You can divide by the GCD by a previous theorem. So you divide this by n over d, you get T1. You divide this by n over d, you get T2. And you divide this by n over d, and you get d. So T1 is in fact T1 and T2 are congruent mod d. Okay? But this implies that d divides T1 minus T2. But T1 minus T2, well, you know what I said? T2 was larger. Why don't we say, so d divides T2 minus T1? But T2, well, note, well, let's write it here. Note that T2 minus T1 is in between 0 and d. If you don't believe that, consider the numbers 0, 1, 2, 3, 4, up to 8. 5, 6, 7, and 8. Okay, so in this case, d is 9. Okay, the biggest difference you can get is by starting with the biggest number and taking away the smallest number. That's 8. That's less than d. And the smallest you can get is by subtracting 2 consecutive numbers. You'll get 1. You can't get 0. So it's bigger than 0. Okay? Bigger than or equal to 0. Okay. So now, what does that tell us? if T1, if T2 minus T1 is less than the common divisor of N and T, what can we say next? Okay, the answer is that this is impossible. Okay, actually, this one is impossible. You can't have D dividing T2 minus T1. So the real question is, what is it contradicting? And the answer is, it's contradicting that T1 is in fact less than T2. So T1 is equal to T2. And that's exactly what I wanted to show. I wanted to show that if any two of these were congruent to one another, they were really the same one. They were actually the same one. And we just showed that. Okay. Now what do we want to show? We need to argue that any other solution is congruent to one of these n that we spoke about. Okay, we need to show that any other solution is one of these. Okay, so how do we do that? And this here was kind of a side note. So that's what we need to show. So let x0 plus n over dt be another solution, of course, to the original equation, which I want to not state incorrectly, ax equals b mod n, which is the same thing as this. Okay, so now we have this other solution, and we want to show that it is one of the original ones. Okay. Now, by their division algorithm on T, by the division algorithm, we know that we know that T is a multiple of T, multiple of D plus a remainder. D is QD plus R, where R, of course, is in between 0 and D. That is what Q can equal. Okay, so now we need to invoke this in here. So we have that x0 plus ndt is equal to x0 plus n over d times t, which is x0 distributing, the q's cancel out, plus nd plus n over d times r. Okay, now that is equal to, or congruent to, n0 plus n over dr plus n over d times r mod n, simply because that's a multiple of n. That is, we just get that. And that's for all r's between 0 and t. Now, what's happening is the following here. Okay, now that you had a moment or two to think about it, notice that R is less than D. Well, this is one of our original ones. Remember, we had x0 plus n over dt, where t fluctuated between 0 and up to d minus 1. Well, that's less than d. D minus 1 is less than d. In fact, this is the smallest number that's bigger than d minus, the smallest integer that's bigger than the integer d minus 1. That is, r is in between 0 and d minus 1. Okay, note that r is in between 0 and d minus 1. Which implies that x0 plus 1 over dr is one of our original d minus 1 solutions. And that completes the proof. If you like proofs like this, subscribe to my channel. Leave a comment, click the like button. See you guys in the next video. Watch and learn.